what are our steps when we're doing an optimization problem? What does it mean to optimize something? Maximize or minimize, depending on what the application is. Usually one or the other is what you're trying to do. Here you go, Anson. You need one of those. So when we're optimizing, we're trying to maximize or minimize some quantity. So step one is kind of like it was with related rates. We want to get a picture if we can. We want to assign variables, what's given to us, what are we trying to find, all that stuff. Step two is where we're going to write the objective function, sometimes called the primary function. That's the thing. You always start with the thing that you're trying to maximize or minimize. You got to figure out what is that, and I've got to come up with some kind of an equation that's, where that's going to be my output variable, okay? That's the quantity that's going to be optimized. So if there's only one other variable, right? Like let's say we have volume of a sphere or something, right? Then volume is my objective function, V equals, and 4/3 pi r cubed, right? Well, there's only one independent variable, r. It's volume as a function of a single variable, r. Agreed? So I don't have to do anything. I can skip step 3 because I've already got my objective function for a single variable, and I can just go right down to step 4, which is curve sketching, essentially, right? We're just going to make a table and we're going to analyze that function just like you guys have been doing with all your curve sketching stuff. Okay, if we end up with more than one, and for you guys more than one at this level means 2, if we have 2 independent variables, then we need to go to step 3 because we've got to reduce that objective function to a function of one variable. How are we going to do that? With a secondary equation. We need some other equation that's going to relate the 2 independent variables. And are you starting to see that this is a great strategy? When you want to eliminate a variable, if I have 2 variables and I want to eliminate a variable from a function, I just have to be able to relate those 2 variables and solve for one of them so I can substitute that one, right? Give me 1 to 5 on that concept. I mean, we've been doing that for a while now, okay? And we'll do it more. But we want to reduce the objective function to a single variable. Keep in mind, and we'll come back to this again and again, the secondary equation, I like to call it an equation of constraint because it's always based on the constraint for this problem. To find the maximum or minimum value, it's what prevents you from just saying, well, I'll make it infinitely big or I'll make it 0, right? It's going to be the number that's attached that constrains the values of the independent variables. And then we just make our table and analyze it. Okay, so this is the one we were working on last week when we started talking about optimization. We said find which points on the graph y equals 4 minus x squared, which is just a downward opening parabola, right? Which points on that graph are closest to the point 0, 2? Okay? And so we kind of, we didn't probably need to do this, but we made a sketch. There's our parabola. There's the point 0, 2. And here's some point on the graph, on the parabolic graph, right? What are the coordinates of that point? X, Y, right? We don't know what they are. They're both going to be variables, aren't they? But they can't just be any old variables. I can't just randomly pick values of X and Y. How come? Like I can't just pick X is 7, Y is 9. Well, I don't know what they are, but how come I just can't randomly pick values? Yeah, it has to be on the parabola, right? The point has to lie on the parabola, so you can kind of visualize that. Think about the parabola as being an infinitely long piece of wire that's just bent in a parabolic shape, and there's a bead that's sliding along that wire. Well, the location of the bead would be the location of the point. So there are an infinite number of possible places that bead could be, but it is constrained to slide on the parabola, right? So let's first of all come up with our objective function. The objective, what is the thing we're trying to find here? What's it want us to minimize? It doesn't even say it, but it's implied. Did you say it? Distance, right? It's the distance between the bead and the point at 0, 2, right? That's the thing we're trying to minimize. Agreed? So we need to come up with a distance function. Well, the distance function, isn't that just coming from right triangle, right? You guys get that the distance formula is the Pythagorean theorem. Which seems harder, the distance formula or the Pythagorean theorem? Don't you think the distance formula seems a little more complicated because it's got square root? You got to memorize stuff, it's got square roots. So don't ever think about it that way. Just think about it as distance is just the hypotenuse of a triangle, always. And, you know, in this case, we're going to call it little lowercase d is distance. Well, what's the triangle? It's that triangle, right? And it's going from, the x-coordinate is going from 0 over to x, right? Everybody agree? So the base of that triangle is just x. Well, what's y doing? The height of that triangle, it's going from y down to y equals 2, right? So the height, or the vertical leg of that triangle is just y minus 2. Everybody see that? And so then by the Pythagorean theorem, we just get d squared equals x squared plus the quantity y minus 2 squared, right? Okay, here's the first trick you can do. Does this question ever ask for distance? It doesn't. What does it want? Closest point, so that's going to be the point where distance is minimized, right? But it never actually asks for the value of distance. Agreed? So to find the closest point, we could minimize the distance function, or we could minimize some other function that's also going to be at its minimum when the distance is minimum. Everybody get that? Do you see such a function anywhere? Lowercase d is distance. If I solve for distance, I mean, that's going to be a little bit of a pain, isn't it? If I solve for distance, look what I'm going to get. Distance equals the square root of x plus the quantity y minus 2 squared. Well, what's kind of ugly about that? You're going to have to do calculus on all this stuff, right? What don't you like about that function? Square root. Yeah, I mean, how fun is it to do calculus with radicals? It's just pain to do, isn't it? You'd rather not, right? So is there a different function that we could minimize here where we could avoid the square root? Yeah. Yeah, let's assign some new function, call it capital D, and it's distance squared. Isn't distance squared going to be minimized when distance is minimized? Because distance is always positive. We're always non-negative at least, right? Everybody agree? Does that make sense? So why not just minimize distance squared? That'll be the function we'll use, capital D. Make sense? That's a great trick. We do that a lot in math. As long as you can solve a different, you can use a different function or solve a different problem as long as you're going to get the same answer, right? If all you want is the answer, who cares? Give me 1 to 5 on that concept. How are we feeling on that, right? Okay, I mean, would it have worked to just minimize distance? Yeah, it would have. We're going to get the same answer, but it's just a lot harder, right? The calculus is harder to do. Okay, what's wrong now with my objective function though? We chose this new function, capital D, to be our objective function. Has 2 variables, right. Okay, it's got 2 variables. Everybody agree my independent variables are x and y. The way we really could write this if we wanted to would be, this is going to be a little different notation. You guys haven't really seen this before, but it's no big deal. This is just capital D of x and y, right? And when you do multivariable calculus in college, you'll deal with stuff like that all the time. But we don't want to do that. We want to make this a function of a single variable. So what do we have to do? What do you think? Yeah, so we've got to come up with an equation that relates x and y. It's already given to us, though, isn't it? What's the constraint here? What constrains in this problem? What constrains our point? We want to find the closest point. What prevents it just from being 0? What prevents the bead from just being right on top of the point 0, 2? Okay, yeah, the wire, right? The graph that's constrained, the point is constrained to be on that graph, or the bead is constrained to be on that wire, that parabolic wire, right? So naturally, that's our constraint, isn't it? That's the thing that constrains the behavior of the point. And so that's our secondary equation right there. They gave it to us. Y equals 4 minus x squared. Okay, well, we can just plug that in directly. Y equals 4 minus x squared. And now all of a sudden, we've reduced our objective function to a function of a single variable, and we're good to go. Then we can just do calculus, right? So we get d equals x squared plus the quantity y, which was 4 minus x squared, wasn't it? Minus 2 squared. Well, that's just 2 minus x squared squared, right? And notice this is now a function of a single variable. Okay, what is that? What's the quantity 2 minus x squared squared? Four minus, no. What's wrong with that?
Oh, shoot.
Right, you can't distribute an exponent when things are being added or subtracted. You got to use a pattern here. What's the pattern?
A squared plus 2ab.
There you go, good. Where a is 2 and b is negative x squared. So what do you get? Well, minus 4x squared plus x to the fourth. Everybody see how we got that? A squared plus 2 times a squared plus 2 times negative x squared, right? Plus negative x squared squared is positive x to the fourth, right? Good? Okay, and then we can combine like terms, and we've got our function. D of x equals, what is that? X to the fourth minus 3x squared plus 4. Agreed? Okay. I want to see what's on the next page. Oh, never mind. Okay, so we need to... Okay, so there's our, we need the domain though, don't we? There's our objective function. Our independent variable is x. What values could x have? Yeah, it could have, right? Isn't that true? X is just the coordinate of the point on the parabola. X coordinate could be anything. Agreed? Okay. So domain is negative infinity to infinity. So there's our x row goes from negative infinity to infinity. And now what? We could try for symmetry. Is there any symmetry? There is, isn't there? What kind of symmetry? Even symmetry. Good. So we know we have even symmetry. Now what do we need to do? Derivative, sure. Okay, so what's... And this is, now do you see the benefit of not solving for distance on this, using the distance function? That's a pretty easy derivative. So what's d prime? Okay. And should we do a second derivative? We definitely should, right? Because then we get to use the second derivative test, which is super easy and quick. And there's a very easy derivative. So what is our second derivative? Minus 6, good. Okay, so let's go ahead and factor the first derivative. How's that factor? Okay. Good. So what are my critical numbers? Good. D prime equals 0 at x equals 0 from that factor, and x equals, okay, plus or minus square root. So it's one big square root if we do it that way, right? That's fine. We'll just leave it like that. We don't have to rationalize the denominator. So I get 3 critical numbers. Let's see, how about my second derivative? It's probably it's so easy to factor. Let's factor it. What do we get?
Factor out of 6, so 2x squared.
6 times 2x squared minus 1. Did I do that right?
Yes.
Yeah, okay. We can just leave it like that. That's fine. Okay, so we get critical numbers at plus or minus square root of 3/2. And it's 0, we said, right?
So I had a question for you.
Yep.
What does the 0 of the second derivative do to the function?
Okay, what's important about zeros? We sort of like call that a second derivative critical number. What's important about them? Okay, they're only places where the concavity could change, where it could get inflection points. Yeah.
Does it always change at those spots?
No, doesn't have to.
Maybe just on both sides.
Right, so it's, because like for example, we've seen quite a few problems like this where like at 0, for example, 0 might be, the number 0 might be a 0 of the first and second derivatives, which means it's a candidate for being either an extremum from the first derivative, right? Because it's a critical number, or or an inflection point because it's a critical number of the second derivative, but it can't be both. It's impossible. It has to be one or the other. Okay. Does that make sense?
Yeah.
Okay, those are zeros of d prime. And so all we need to do here is just check the sign of the second derivative. What's the sign of the second derivative at 0? The second derivative at x equals 0? Oh, yeah, you're right, negative, yep. Okay, yeah. No, you're good.
0 minus 6.
Negative. Okay. What do we get at, okay, yeah. What do we get at plus or minus the square root of 3/2? Sign of the second derivative.
3 halves times 12. It's bigger than 12, so positive.
Positive, right? Right. That's going to make that term bigger than 1, right? Everybody agree when I plug it in? Okay, so I get positive, positive. So what's going on there then?
Wait, let me see.
So what's happening here?
Happy function,
Happy,
sad,
sad, happy, right?
so the minimum.
Right, so the point at 0, the point when x is 0, that's actually a relative maximum for distance. And we get relative minima, and the only other extrema are minima, so they have to be global, right? I mean, they're going to be the smallest minima. And so what's this thing, if we did sketch it, what does it look like? Okay, and I guess we could plug in some points. This is the point 0, 4. These are the points what? So if I square, we have symmetry here, don't we? If I plug in square root of 3 over 2, I'm going to get 4 minus 3 halves. So that's 5 halves. And we don't really care though, right? Because it's not distance, it's the distance squared. Distance would be the square root of that, right? But it never asked for that. We just need to know what's going on there. Well, those would be places where right, our function's doing something like this. So those are going to be minima for our function, and they're also minima for distance. So they happen at those places. Does that make sense? Okay. So if we went back and actually answered our original question, at what points on that graph are we closest? Well, we're closest at when x equals plus or minus the square root of 3 halves. And then I could plug those in and find the y values. Okay? Make sense? Okay. I guess let's do that, huh? We probably should do that. So y so we get the point square root of 3 over 2, 5 halves, or the point negative square root of 3 over 2, 5 halves. Those are the places where it happens. Okay, give me 1 to 5. Does that make sense? Okay. Okay, what about one like this? We'll at least start looking at it. Find the dimensions of the open, and this seems like a weird question. We'll just set it up. That's all we're going to have time for. This probably seems like a very weird question, but this is in every first-year calculus textbook that's ever been written, the same kind of problem. Find the dimensions of the open rectangular box of maximum volume that can be made from a sheet of cardboard 19 inches by 11 inches by cutting congruent squares from the corners and folding up the sides. So do you see what what that means? So it's like, here's our piece of cardboard, and what they're doing is that, right? Well, how did they do that? They made some squares out of the corners here. Let's see, I'm going to try to make this look nice. So I'll do like this. Let's just say that's our square for some reason. So I'm saying those are the pieces I'm cutting out of the corners. Everybody get that? That's everything. We're going to throw them away. Cut those out and throw them away. Everybody see that? Okay, and then we're going to make some folds. How do I do this? And I want... So there's a fold, there's a fold, there's a fold, there's a fold. Everybody see that? And then I'm gonna fold along those lines and just fold up the sides to create an open box. All right? Everybody see that? Okay. Go. What can we do? Can we put some numbers in?
Yeah, so we know the distance of the cardboard.
Okay. So then doesn't that mean that this distance is 19, right? And that distance is 11, right? Okay.
Okay.
Is there anything variable here?
Yeah, the length of the boxes.
Yeah, I get to choose the size of the square I'm cutting out. That could vary, right? So what should I call that probably? Good, let's call that x. So if we call that distance x, well then that distance is x. Where does that show up on my folded up box?
But it's gonna be like the height is what, 11 minus 2x?
Yeah, everybody see that?
And the width is 19 minus 2x.
Right, so yeah, so when I fold it up, x ends up being the height of the box, doesn't it? Everybody see that? The length of each of those, or the side length of the squares that I cut from the corners determines the folded up height of both sides of the box. It's the width of the flaps that I fold up, right? So this distance is x. Yeah, what's this distance down here going to be then?
X minus.
19 minus 2x.
Yeah, it's going to be, that's just going to be the distance from here over to here, right? Which is just the total distance, 19, minus 2 of those x's, right? So 19 minus 2x, and then this distance, just 11 minus 2x, right? So this ends up being a pretty easy problem, actually, because we're trying to maximize volume. Well, what is my volume? My objective function is volume. So what's volume? Yeah, it's just x times 19 minus 2x times 11 minus 2x. How many variables are in that? 1. That's v of x. So this is going to be a pretty easy question, right? I'm just going to, what am I going to do to this function? Because I'm going to have to differentiate it, right? What do you mean by that?
Like foil.
So I'm going to expand it out. The word we'd use in math would be to expand. When you want to multiply out factors and you want to write something in expanded form, in polynomial form, or with everything already distributed, that's called expanding it. Why expanding it? Because usually it looks a lot bigger after you expand it, because you have a bunch of terms. Okay, so if we do that, we can just FOIL this out, and then when I distribute the x, it just raises all the powers of x by 1, right? So what do I get when I FOIL this out? Yeah, what's 19 times 11? 209, good. So I get 209. I'm going to end up with an x when I distribute. What if what's that? Minus 18x, or sorry, not 18, minus 38x, minus 22, 38, 22, good. And that's going to end up being an x squared when I distribute. And then finally, x going to be cubed then, right, when I distribute the extra x. Good. Okay. I can't probably factor that, can I? Okay. So that's my function. I mean, I'm stuck with it, but that's okay. I mean, when I differentiate it, it'll get a little bit easier, right? A little bit easier to work with. Okay, so what's my domain going to be?
Oh, no, it can't be
Ah, it can't be all reals, can it?
Or it can't be
zero
negative. It could be
plus.
negative. It could be
Well, I mean, if it's 0, my box doesn't hold much, does it?
Zero plus.
I mean, we could say 0. It's fine. 0 is not going to be our answer though, because certainly but that's the lower limit of, right? But what's the upper limit? Not even 11. Remember what we did with, there's a good way to think about this. These get confusing. But when we did related rate stuff, remember that a lot of times when we were doing related rates problems, we had the same issue where we'd have multiple variables, right? We'd have multiple independent variables. What always happened with those, as one variable went up, the other one went down, right? Okay? So same kind of thing's going to happen here, right? When we calculate volume, we've got height times width times length. Just imagine, and just get good at this, just kind of do a little animation in your head. What's going to happen to the dimensions of the base as we squash down the height? It's going to get wider, isn't it, right? Okay, what's going to happen as we squeeze this dimension together? The other ones would expand a little bit, right? Does that see what I'm saying? Okay, so what's going to be the constraint here, though, right? I can only squeeze these dimensions down to 0, right? When would I run out of room to squeeze this box from front to back? Like what value of x would... See what I'm saying? I mean, the width here is 11 minus 2x. Yeah. So it's 5.5, right? Everybody see, that's the biggest x could be. That's the biggest I could cut my corners would be if when the corners met right here, I can't cut my corners can't be any bigger because there's nothing left to cut. Now, I wouldn't ever get there with the 19 because 5.5, I mean, see what I'm saying? 5.5 is as much as I can do. And when I cut 5.5 out, there's still going to be a little bit of width left to the box here when x gets really big. Everybody get that? But I've extinguished the shorter width when x gets to 5.5. So that's the upper limit, isn't it? So our domain, x, just goes from 0 up to 11/2. That's it. That's the limit of the possible values of x that I could choose. And then from there on out, we're just doing a little bit of calculus. So what would we do next? Derivative, yeah. Okay, so v prime. I'm gonna flip this around and write it in standard form. So I'm gonna get 12x squared minus 120x plus 209. Agreed? Okay. Should I do a second derivative? Why not? So easy to do, why not? So what, 24x minus 120, which is just 24 times x minus 5. How would I find my critical numbers? Yeah, quadratic formula. Yeah, right? Okay, so then what would I get?
120. Minus square root of negative 120 squared.
Well, so just 120 squared. Right.
4 times 12 times 209.
Okay, all over.
24.
Okay, what's that give us? Somebody got a calculator handy? Just throw in the positive one first.
Divided by 2a. A is 12. You can't see the original.
We need to watch the
A was 12.
I think we need to watch the song again.
Yeah. You see that A was 12?
Come back. Yes.
7.75.
So we get about 7.75. Okay. It's not exactly right, is it? No. Or what else?
Negative 330.4.
Okay, what do you think about that one? It's probably not it, right? Okay. So about 7.75. Hold it. That's not right. Is that the plus one or the minus one?
7
Yeah.
at plus.
Okay, the minus one, I think it's going to be bigger than 0. Definitely. Because this is, you agree, this has to be smaller than 12.
Yeah, I got 2.24, or 2.25.
Okay, there you go. Okay, are those both good? What's wrong with the first one?
It's outside the domain.
It's outside the domain. So that one we could cancel, right? So we only get one critical number at about 2.25. It's a 0 of the first derivative, right? Okay, what's the sign of the second derivative at 2.25? Negative, exactly. So what is this? Yeah, it's a maximum. There's only one maximum in our domain, so it's the maximum, right? Everybody see that? Okay, hey, we made it. What do you know?
Was number 2.25 just a coincidence?
Yes.
Okay.
Yeah.
Is there any chance you could